You all can see?
Yes.
Okay. This is lecture 8. Today is 24th. Today, we finally come to the crux of the essence that does it all, of the standard model and the modern field theory, the Higgs mechanism. We studied up to today a U1 global symmetry. We studied with the following Lagrangian. We can call it Nambu-Goldstone, which was 1/2 d mu phi star minus a potential minus a Yukawa interaction. We chose the potential to be λ/4 phi square minus v square, everything square. We are going to keep that. Again, remember the sign implies spontaneous symmetry breaking. And the Yukawa interaction is the fermion scalar one. So it was the Yukawa coupling psi L bar, psi r, phi. It's a chiral theory. Left and right fermions transform differently, obviously. This theory has a symmetry actually. There is U1 chiral, there are two symmetries. Phi goes into e to the I alpha phi. And I can choose any combination I like. So I chose psi r e to the I minus alpha over 2 psi r, and psi l e to the I alpha over 2 psi l. Notice it's chiral. Left is different from right. Chiral U1, left is different. There is also U1 vector, like we called. Phi does not transform, and psi L and R transform the same way. This is simply a fermion number. So this is vector-like U1. Left is equal to R. We found out the theory told us that phi, which I often call, well, there is a vacuum manifold. Let's put it that way. Vacuum manifold, phi 0 square equal v square. It's a circle. A set of all points that minimizes the potential. This is vacuum manifold. It's a circle that implied the following. The field I chose, these variables we can always think of the changes, but for the moment, let's take this. There was, let's call it phi, how shall we call it? Phi 1, phi, the first set of variables. We also said we could write, and we'll come back to it. That's another possibility. Both are very interesting. We'll study both. We found out, no matter how we write this, that mg is 0. mh squared is 2 lambda v squared. M fermion, m psi is Yukawa times v. We had spontaneous symmetry breaking of, in other words, we have spontaneous symmetry breaking of U1 chiral. That is broken. The vector-like is not broken because the scalar field does not transform. Phi goes to phi, not to 0. Breaks U1 chiral, but U1 vector-like is preserved. It's a beautiful mechanism. It has to do with the fact we said, I mean, what we really said, that what happened here, if I write phi e to the I alpha q phi, that means that q phi is just phi. I took charge 1, and that implies that q phi 0 is phi 0. It's not 0, which implies that vacuum, the symmetry is broken and vacuum actually carries charge. It's not vacuum. It's a very interesting world in which you would live. However, we don't have a candidate. Nobody's ever seen a Nambu-Goldstone boson. This is not what we are after. Also remember, our problem was the physics of massive gauge boson, the Procca theory. So of course, the logical thing is now to stop here. Instead, we'll gauge U1 chiral, not the vector-like. In other words, we are going to say that alpha is alpha of x. For we are after, so that we have U1 gauge theory. And it's a chiral, just like the standard model, chiral gauge theory. That's why I took this example. So everything that concerns with the sort of essential features of the standard model, as I was telling you, and I keep repeating it, is captured here. So if you pay attention here, you will get a good starting background. What does it mean? This is called the Higgs Lagrangian. Nambu-Goldstone becomes the Higgs Lagrangian. Higgs theory, let's call it. It's often called Higgs theory. It was not studied just by Higgs. Tell you what, there are other people who studied Angler, Braut, and Angler around the same time. And some other people, Angler actually shared the Nobel Prize with Higgs. And we are talking about 1964. A few years later, after Nambu and Goldstone, and 3 years after Glashow, now we already have the electroweak gauge structure, but we have a problem with the breaking. And what it means, if I do that, it's very easy. The Higgs Lagrangian is basically the same, as you know. All I have to do, oh, I forgot here, I'm very sorry. Nobody told me that I missed something. What did I miss in my Lagrangian?
Is it F mu terms?
No, how can it be F mu terms? Where is the? I started with a global symmetry. I mean, Higgs mechanism is the title of the lecture, but I start with a global symmetry. There is no gauge field. I didn't miss that. Nobody can see. I need you awake. Maybe you need an extra coffee in the morning. I'm talking about the fermion field. Now, please pay attention. I need you awake. How can I write a field without kinetic energy? That's not a field. That's nothing. It's some object sitting there that you know doesn't have to do anything with our world. So what I missed was a kinetic energy. Just to remind you, which is, of course, let me write it separately. Just to be sure that you remember that there is left and right. This should not have been missed. So all that I have to do, what is it that I have to do, please? To make it a gauge theory?
Upgrade the derivative to the covariant.
Right, that's it. And then, did I have a half here or not? Okay, people sometimes don't put half for the complex field, but I put it. Just a question of normalization. Anyway, so thank you. What I have to write is d mu phi star, say, doesn't matter which order, d mu phi. And of course, the same potential v of phi. And I have, now let me not forget the kinetic energy, psi L bar gamma mu d mu psi L. So let's use the space better. All I have to write is a covariant derivative. And I made it. There is, of course, Yukawa. I don't have to write them. I'm going to keep the same theory. And now, thank you, yes, I shouldn't forget the kinetic energy, the Maxwell-Lagrangian for the gauge field, because I have just introduced the covariant derivative, which we can write like this. It has a universal form. And we have a symmetry. Each field, phi transforms as e to the I alpha q phi. Psi L transforms as e to the I alpha q psi L, and so on. Everything transformed the same way with the fact that q acting on phi is phi. Q acting on psi L, we said, was minus a half, and q acting on psi R was plus a half. This is these are the charges that I took. And of course, here, what was very important, that alpha is a function of x in these transformations. All you have to specify the charges. And when you have a U1 theory, it's up to you to specify the charges. You have the freedom. And we know that, of course, there is a symmetry that I wrote here. As long as a mu transforms is, I missed the coupling constant that I can introduce, of course, because I will have an interaction. A mu transforms in a mu. minus 1 over g, as you know, d mu alpha of x. This is the transformational symmetry. This is my U1 gauge symmetry. This, I hope, is clear, right? But please ask questions now because we will proceed. This is just like QED. The only difference from QED, very profound when it comes to fermion, that it's not left-right symmetric. It's not a vector-like symmetry. The left and right charges are here. The way I chose them actually opposite. So this is surely not, I mean, that you shouldn't get confused. I don't want to break a U1 electromagnetic charge. Left is different from right. Now notice what happens immediately. I'm gonna write again. I can do any which way to write, but let me write the way I wrote originally. If I write this, what happens? D mu phi is d mu h plus I d mu g minus I g, q is 1, a mu times v plus h plus ig. Am I right? There is the derivative piece. No, I'm not right. Nobody's correcting me. I need you more. D mu phi is d mu h, I forgot h, minus I d mu g, y minus plus. The way I wrote, I have it this, okay. So my kinetic energy 1/2 notice I will have, well, let's organize it a little bit, will be 1/2. So let me write like this. D mu h plus g a mu g. I write the real part plus I d mu g minus g v plus h. Absolute value square. I've just separated the real and imaginary part. So notice there are all kinds of terms here, but notice that I will get the, I first take the, I'm interested in kinetic energy. That, of course, you expected. There will be a piece 1/2 d mu g square. Then there will be all kinds of interactions. But I'm interested particularly in this piece. No, I'd rather write like this. I'm sorry. There is an interesting piece, notice, which is, I have missed a mu. Again, nobody's telling me. I don't see you, so I don't know what you're doing. This is a disadvantage of, there are nice things of doing online. But what I had here, what was this? I d mu g. Then I had minus, I forgot a mu. So there is this piece which is very interesting. 1/2, notice g square, v plus h square, a mu square, plus all kinds of terms I'm not interested in. Why? This, of course, is trivial. This is just kinetic energy. I don't care about that. I know there are degrees of freedom that are propagating, okay? So in other words, this is kinetic energy plus 1/2 g square. I'll take v square out, 1 plus h over v, everything square, a mu, plus all kinds of interesting terms to come later. This is what I'm after. I hope you're following me here. This is the most interesting term. What do you see here? So this term, which is the central term of the Higgs theory, is 1/2 g square v square a mu, the first term. Then there is g square v h a mu, and then there is a quadratic piece, which I'm not interested in. There are various terms here that we'll be studying in the days to come, but now we are after the essence. What is the first term? What is this?
Mass term.
Right, we got it. We have generated, this is the celebrated Higgs mechanism. We have a mass term for a MA is GV. This is what I promised to you. When you have spontaneous symmetry breaking, what happens? The particle masses are proportional to V. This is the scale. This is the only dimensionful parameter. So of course, MA must be proportional to V. This is the scale argument. And the proportionality, of course, is coming. This proportionality is coming from the interaction. And that, of course, is a gauge interaction. For fermion, the interaction was Yukawa. Therefore, the fermion mass was proportional to Yukawa. Here it is. For the Higgs scalar, so here the interaction was coming from Yukawa. For the Higgs scalar, the interaction is the quartic one. It's the self-interaction, the lambda. So we have obviously a theorem. In the Higgs mechanism, everybody gets the mass from the vacuum expectation value of the Higgs field, and your mass will be given by the way you interact with the Higgs. Remember what we found out before? Before we had that Yukawa is m over v. So Higgs interacts proportional to the mass of the fermion. In this case, the fermion. MH square is 2 lambda v square. So lambda is 1/2 mh square over v square. And this is the way Higgs interacts to itself. This is self-interaction. Again, proportional to mass. In this case, square. It's a way we normalize. I could have called this lambda square and then it would be linear. It's just a question of the way of writing, okay? But the principle is the same. Notice that in the case of the gauge boson, Ma is GV. And therefore, if you look at the interaction here, the one that I kept. This is very important also. The Higgs interaction. So this was the mass term, and this is the interaction. And it's given by G square V. In other words, we have a term. So notice we have a term which is G square V H A mu. This is why I kept this term. This is nothing but G Ma H A mu. The coupling of the Higgs to the gauge boson, again, interaction proportional to mass. So Higgs gives you mass if you're elementary particle, not you, not to you and me. We'll talk about who gives the mass to you and me. We'll start when I talk about QCD. But at the moment, I'm in the world of elementary particle. There is a very simple rule. You get a mass if you couple to the Higgs. It will give you the mass, and then it will couple to you proportional to the mass. It's similar to the way gravity couples to static objects. If you don't move, gravity couples to your mass. If you move, of course, then the energy enters. Now, Higgs doesn't care how fast you move. All it cares that you have a mass. So you may be moving like crazy. You may be the photon. You're moving with the maximal speed of light. Higgs won't couple to you because you don't have the mass if you're the photon. That's very important, the Higgs mechanism. So the essence of the Higgs mechanism. Elementary particles get mass from the vacuum expectation value of phi, where phi is phi plus h and so on. H is very important. And h, the guy that lives around the wave, couples to the mass. Here it is. From now on, the rest will be details. Highly profound details, but here is the essence of the story. And we can see that there are other interactions. For example, I didn't write h squared and so on. I was interested in the leading effect. The leading effect was the mass and the interaction. So it sounds exciting. It's beautiful in a sense because all particles get a mass from the same origin. But remember, we started with the following. I mean, why am I doing the Higgs mechanism? Well, you can tell me because there is a Higgs boson, so why are you bugging us with history? Well, to appreciate, you need to understand that we needed the Higgs mechanism. It was there for theoretical reasons. And somehow, amazingly enough, it was there so just that we would be able to compute. And yet the nature provides this Higgs mechanism. There is something, unreal a bit here, touching the way it worked. And you say, well, you made it. Say, okay, now basically, just generalize this to the standard model. What else do you have to teach us? Well, it all looks beautiful up to now, but notice I start. Stat with Proca. Remember, there was no need for any Higgs. I knew how to do the gauge theory. I started with Proca, and I say the Lagrangian is and then I added a mass term. I know how to work with Proca theory. And of course, if there are fermions, I know how they couple. I had a complete theory. There was no need for the scalar. And this is why a lot of people resisted introducing a kind of beast that never existed before, that apparently, was just a complicated, redundant way of doing the same thing. Everything was okay here. But what I found out that the propagator was the following. Minus I, k square minus ma square, remember? That was good. G mu nu, that was good. There was this piece. The propagator. We didn't like it because it had this piece, which is bad. Goes to 1 over m square when k goes to infinity. Because k mu is basically k square in symmetric integration, and therefore you get 1 over ma square. Okay. But now what I achieved, so what I traded here by doing the Higgs, this was Proca theory. Higgs. Well, you can complain. Well, what did you gain? At the end, you have a massive gauge boson. It's equal to G times V. Okay, that sounds beautiful, but it is still a Proca field. So you will say, look, the delta mu nu in the Higgs theory of A, we could have said here, of A, again, will be delta mu nu of Proca, because I will compute it the same way. The guy is massive. So it seems that the problem of MA persists, the Proca problem. This is where, so 1964, Higgs will introduce the Higgs mechanism. He will write another interesting paper on the Higgs I'll tell you about. And that's basically all. It's a very strange career of the guy who gets a Nobel Prize, writes a couple of papers. In 1967 and 68, they used the Higgs mechanism, Weinberg and Salam, in a beautiful paper. Weinberg actually introduces precisely the Higgs doublet of the Standard Model. So in 1967, now we have the Higgs in the Standard Model. This is Weinberg paper. And Weinberg gets stuck. Proca problem. We'll come to why Weinberg got stuck. Everything will change when in 1971, with a stroke of a genius, a young graduate student finds a solution. At Hof solves the Higgs-Particle problem. And that's what I want to talk about. I will not give you the full theory, but I'll give you the flavor of what has to be done and why the problem persisting and how the beauty of spontaneous symmetry breaking gets around it. So let's try, in order to appreciate all of that, let's try to see what we have achieved. So let's go back to what we have achieved. We have a massive gauge field, but notice what happened. I started with a complex field phi, and let's forget about the fermion. So let me just do this. Forget the fermion. I don't need it for the time being. I'll come to it, of course. Fermions are the building blocks of the universe. But let's forget the fermion. In this case, this will be the Higgs-Lagrangian. Let me just write symbolically minus the famous potential spontaneous symmetry break minus the Maxwell. The how many degrees of freedom do I have? Who can help me count? 5. How many degrees of freedom?
1, 2.
No, 2. We count real degrees of freedom. I should have said that, but that's what we do. We must have a way of counting real degrees of freedom. Otherwise, the real scalar will have as many degrees of freedom as complex, and we can do that. 2 real degrees of freedom. And a mu?
Two.
Right. Why? Because it is massless. There is no mass term. Therefore, we have 2 real degrees of freedom corresponding. We know what it is. It's helicity. Photon has 2 degrees of freedom. You can't stop this crazy guy, no matter how fast you go. So we can't actually talk about spin, but you can talk about helicity. Remember, helicity is simply the projection of spin on your directional motion. That's well defined. So I have 4 degrees of freedom. This is what I started with. But then something happened. So this is my beginning. But then I said there is spontaneous symmetry break. And what happens is I just convince you that MA is GV. I got the Procca field. How many degrees of freedom, Proc?
3.
3 degrees of freedom. This is spin equal 1. We actually constructed the states that corresponded to spin equal 1, manifested the 3 of them. We took it at rest. We can always do that. If the guy moves fast, so do we. We stop it there. It stops in our rest frame, and we have 3 degrees of freedom. So I got an extra degrees of freedom. I'm like a magician, you know, that takes a handkerchief and the pigeon comes out. How in the world could I produce an extra degrees of freedom? That cannot be. What's going on? We have to understand what's going on. And here, to understand what is going on, you have to choose the right variables. This is what Weinberg says. When you count the variables, you can be confused. Are you saying, but what in the world are you talking about? Look, we wrote phi as V plus H plus IG. This was our first way of writing. And we found here before in the Nambu-Goldstone theory that this was a physical scalar field with a mass 0. So we're saying, how are you going to avoid that? What's going on? It seems to be true. But there is a but. I can also write 5. I'll take the second way of writing. I just like to choose different variables. I gave them the same name. I'm a little here careless. But just for you to appreciate, look, if I expand this, the leading term, this will be V plus H plus IG over V times V plus other terms. V cancels. So the leading terms, these two ways of variables would agree. That's why I use the same name, just not to put primes. So let's now do this. Let's look in this. Remember that I have a symmetry. There is a gauge redundancy, if you wish, gauge symmetry. I can rotate, choose the phase of phi any which way I want, as long as I go from a mu into, but it's just a renaming my gauge field. If I have that symmetry, why don't I choose alpha is minus G over V? Any alpha works. It's a function of X, as G is. Choose this. In other words, phi goes into e to the minus G over V, V plus H, e to the IG over V. Look what happened. I get V plus H. I should call it phi prime now. And a mu goes into something that you could call the mu prime, which is a mu. I have to, don't forget that, which is 1 minus G d mu. There will be plus G over V. That's some a mu prime. So look, if I look at the a mu prime, and I have to write, I have the right to do this. I have 1 degree of freedom here, real. V plus H, there is just H. And I have here, it's a massive field that I've checked, 3 degrees of freedom. Well, 1 plus 3 is equal to 4, which before was 2 plus 2. I actually have only 4 degrees of freedom. Really, what I've learned, G is not physical. It does not exist really. It was physical when the symmetry was global, because I was not allowed to perform this rotation of the phase. The same way, remember, this is very similar to the photon, okay? When you worked in the gauge in QED, this is very similar to QED. In QED, you have a mu, which apparently has 4 degrees of freedom, but no, you have a redundancy because of the gauge, freedom of gauge transformation. So from a mu, which has 4, you can actually go by gauge rotation into a mu physical, which has 2. The physical field has 2. And you do that by gauge, fixing gauge transformations, whatever. You eliminate the degrees of freedom which are not physical. So you see, for example, what does it mean that longitudinal photon, for example, you can never produce it. It doesn't exist. You may work with all 4 of them, but at the end of the day, you will see it doesn't get produced. Same thing here. You may think that there is G, but that degree of freedom is redundant. It's not physical. By the way, this gauge, this is called the unitary gauge, or sometimes people say physical gauge. This is called unitary or physical gauge. This is very important. where you work with phi equal V plus H. I will not put prime anymore. And A mu massive, 3 degree of freedom, non-zero. I will get rid of prime. This is, for example, the way Weinberg worked. Notice this is beautiful. A unitary gauge or physical gauge where you can read which are the physical degrees of freedom is extremely useful. So this gauge, you can get immediately the physical picture. The physical degrees of freedom, the real, true degrees of freedom. So if you want to see what your theory is describing, go to unitary gauge. That's what. So this is this choice of variable. Choice of variables. You always have a choice of variables. Remember, so I've chosen the variables to go here in the unitary gauge. And it seems that I've done something smart. This is what Weinberg does. And if you wish, this is a smart person's approach. It takes some thinking to realize that G is not physical. But you know what happens, what we say, by the way we say it. So where did G go? So you are asking me, but there was G in the Nambu-Goldstone case when alpha is constant. You get that G is physical. G exists. Mg is 0. It's this Goldstone or Nambu-Goldstone boson. So where does it disappear? Well, we say that A mu eats G. A mu became fat. He had 2 degrees of freedom to start with. This guy had to get a degree of freedom from somewhere. And that's what he did. It sort of incorporated the G in itself. You can see that manifestly when I performed the gauge transformation. You see G entered into the existence of my mu field when I chose this rotation. He made part of it. Okay. So in other words, G becomes a longitudinal component of A. That's very important. This is sort of the crux of the Higgs mechanism. You and I, for all that we know, would simply forget that G ever existed. Field H is called the Higgs field. H is the Higgs field. When other people introduced the Higgs mechanism, like Prout and Aglaire, they didn't have the Higgs field. Actually, the story is very interesting. Higgs writes the paper in the summer of '64. Higgs sends a paper. Higgs has the Higgs mechanism. Higgs mechanism is giving gauge boson a mass. The referee rejects the paper. He said, you should, in order to make this really exciting, you should think of some physical consequences. For example, your scalar sector. This is very interesting. This is an amazing, the referee was Nambu, one of the greatest physicists. The idea of spontaneous symmetry breaking and many others, I'll talk about Nambu a lot. The father of it all. It actually reveals, Higgs wrote about that. Nambu tells, as a referee, it's amazing, instead of he writing this, says, think of the scalar sector. And then Higgs says, oh yes, I see the, Higgs says, Higgs says, oh, I have a Higgs boson What do I mean by the Higgs boson? Well, if phi field goes through the spontaneous symmetry breaking so that phi is non-zero, then phi can be written as 5 plus h plus whatever else is there. There will be imaginary component with mh be given by 2 lambda v squared. This is the Higgs particle. Higgs notices this, encouraged. He sends another version that makes history and he gets a Nobel Prize. This is how the world interpreted it. But remember, Goldstone noticed this. Goldstone had H. Because the existence of the Higgs field does not depend whether you have a global or local symmetry. It's in the potential. Potential doesn't care. I mean, who cares? Whether, look at the potential. Potential doesn't give a damn whether you're global or local. It's one and the same potential, of course. There are no derivatives in the potential, therefore you cannot know that the symmetry is global or local. There is a great irony. A typical injustice that can occur with Nobel Prizes, okay? Sometimes it's really insane that Goldstone didn't get a Nobel Prize. It bugs me. By the way, when you think of Nobel Prizes, this is a side effect. So Goldstone doesn't get a Nobel Prize, okay? And this is crazy. There are other things which are even more crazy. Do you know who is the father of quarks? Look at this, just I'll make a side remark. Who is the father of quarks? This is the essence of your field. Who is the father of quarks or fathers? You don't know? Huh?
I know Gell-Mann proposed the SU3 symmetry.
Not SU3. I don't care about SU3. I talk about quarks. SU3 was before the Eightfold Way. The quarks are suggested by Gell-Mann and Zweig. This is very interesting, by the way. This is just en passant, so that we relax for a few minutes. Unlike Gell-Mann, Gell-Mann is a professor at Caltech, an extremely famous particle physicist, a colleague of Feynman in 1964. This guy is a graduate student, Zweig. Gell-Mann doesn't take them seriously. He thinks they're a mathematical entity, nice to organize the SU3 symmetry of strong interactions, the existence of pions and kaons and other beasts. Zweig takes it seriously. The world doesn't pay attention. They won't publish his papers. He writes 2 beautiful papers. It's mind-boggling. He never got a Nobel Prize. If you think about that, maybe you heard that Kobayashi and Maskawa got a Nobel Prize for the top and bottom quark as a part of the CP violation. I'll remind you that. I'm sure Alexei Maskav told you about that. They got the Nobel Prize for suggesting 5th and 6th quarks, but the father of quarks never got the Nobel Prize. This is... So when people talk to you about prizes, you know, keep this in mind. Prizes are given by humans. And often they are true reflection of who did what, but they are sort of crazy counterexamples. I want to see if there are questions. I've actually tried to mobilize the word. I don't know if you're interested, but I can't help to tell you to give Zweig a prize. I've tried to I've been in a great correspondence, and a couple of years ago, Weinberg invited me to Austin, and we had some clash over the theory of neutrinos that we'll talk about. So I try to, if I suggest it, he won't make it. You need a Nobel Prize winner. I've tried to use the people I know, Wilczek, Weinberg, and at Hoft. They don't seem to care enough. They kind of mumble that they would, but it seems that they didn't move. If these people were to move, I think Zweig could get a Nobel Prize. I find this disturbing that a great physicist like that, the father of everything that we do, has to do with quarks. That's the crux of our field. If you don't have any question, we'll make a break, but maybe it's, you wanna. Okay. If it's not urgent, let's meet in, let's take a nice number in 12:05. Maybe in this 6-7 minutes, you get an idea what to ask. Okay, we are back. Questions? As I told you, as Weinberg puts it nicely, it's all about choosing variables. Remember what Weinberg says, make sure you guys choose right variables. Otherwise, you will live to regret your choice. The choice that Weinberg makes, the unitary gauge prevents him from going on because he has a bad propagator. He can't do the loop calculations. He cannot show that the theory is normalizable. It's manifestly non-normalizable, it seems. It's very interesting. Weinberg says it always. He'll tell you, he says it in his talks. He gave us he's an old friend of ICTP. He was a good friend of Salam. So he often gives colloquia to ICTP even. And, oh, what happened? I'm sorry. He says to these days, whenever he does something stupid at home, his wife tells him, shut up, you couldn't even normalize your own theory. Okay, he chose the wrong variables. Comes at Hoff and says the following. I mean, it's deeper than that. There is a lot of things that Hoff has to do. It's amazing to work, the technical aspect and so on. But the bottom line is here. Why don't I use this variable, says Hoff. As if G is there, but you tell him, look, you moron, why would you use this variable? G is not physical. Weinberg just taught you that G is not physical, you can rotate away. So why would he use these variables? And remember what we do. So immediate analogy with QED. In QED, you don't work with the physical variables. You do not work with a transfers only, which has 2 degrees of freedom. That would drive you crazy. It's not good for computations. What you do, you work with a mu. And then use the gauge freedom to fix the gauge. And you must fix the gauge because we are using unphysical degrees of freedom. It's sort of like using Lagrange multipliers, okay? That's all that the gauge freedom tells you. Not all 4 can be. So you see, you have 4 a mu, and then you go to 2 physical. So what Hoff says, so this is QED, this was the analogy. So what Hoff says, now I have, when I think I have a mu plus G in my theory, that's 5 degrees of freedom, but only 3 are physical. It's very similar. Notice, it's very similar to what we do in QED. Complete analogy. This is a stroke of a genius. Stroke of genius, not of a genius. Stroke of genius, a touch of a genius. With a stroke of genius, he does this incredible thing. Once again, I make a digression. So what do I do in QED? I add the gauge fixing term, which is, this one is quite nice. I take d mu, a mu square. I have xi parameters so that I can check the gauge freedom. right? So 't Hoff has to do the same thing. So here, by analogy, at Hoff says, I need gauge fixing. I need to add gauge fixing term. So you add the, so I will add a gauge fixing term, and I'll do it by the, I don't know whether we put a plus or minus sign. Who remembers? Just a convention. I don't remember what I wrote originally. I mean, it's a convention on psi. No, but so why don't I just take plus sign? Why do I have to take a minus sign? Or maybe there is a minus sign by convention. Someone gonna help me? Wasn't that in the homework?
In homework, it's minus.
I took minus sign in the homework. But that's what I need you. I mean, are you there with me? Or you just, you know, reading a book or something? If I use the minus sign, let me stick to the minus sign. So I'll do the same thing. How will I generalize it? Well, I have to get rid of G. I have to invoke G in this, in the thing. I'm just going to include G here. But they must have the same dimensions, you agree? So I will, d mu a mu has a dimension 2 of mass, because the derivative also has a dimension. So I'll write like this. And I will put, in order to emphasize it, I should have given myself a little more room, plus psi MAG. Square. Analogy with QED. Very useful gauge, this one. We'll have xi parameter to deal with. G is not a physical field, so you see, xi is introduced in order to take care of the fact that it cannot be physical, it's not going to be produced. This is very important. This is just the usual gauge fixing because I'm working with some extra unnecessary degree of freedom, which is minus, let's write it down, minus 1 over 2c. That's what you did in the homework. You must have done it before. What else do I have here? Then I have minus, let me take G separately. What will I have? 1/2 C MA squared G squared. You agree? That's the piece for G. And then there is a mixed term. Now you'll understand how I chose it. And maybe I have rushed, but let me write it still. What is the mixed term? Half goes away, C goes away. So I got A mu, D mu, A mu. Maybe it's not the way I wrote. Now I regret the way I wrote. So let me stop here and then MAG. Let's pause because I rushed ahead of myself. Because what I should have told you, why he had to fix the gauge. Let's just go back. What did Hoff do? He chose this variable. If he chooses this variable, remember, I should have written this from phi. I should have written this before. We'll come back. I apologize. Then 1/2 d mu phi square is what? I wrote it somewhere below. Let's go back in order not to write too much. And we can think when I'm doing it, where did I have it? Start with Roca, so it must be coming soon. Notice this piece here. I need a piece which depends on G. So I'm gonna copy it We already wrote it. It's 1/2. There will be d mu g minus g a mu. There was v plus h. I don't care about h. I'm just looking at the quadratic piece plus other terms. There are all kinds of other terms here. This came from the covariant derivative. Notice what it gives me. It gives me 1/2. This should have been written before. Minus, this is a kinetic energy of G that I wrote. There is a famous mass term plus 1/2 ma square a mu, the Higgs mechanism. Ma is GV. And then there is a piece minus sign. Help me not to make a mistake, please, which is d mu G. GV is Ma, Ma, A mu. Everybody's following me, please. You see how I rushed before? I can make a mistake. It can be a misprint. It can also be a mistake. I think the sign is correct. People agree with me?
Yes.
Okay, let's rewrite this term here. This term is very important. You agree that I can write it as minus d mu of everything plus ma d mu a mu times g. Agree? I will get rid of this. It's a total derivative. I don't need it. It's not affecting any of my equations of motion. So I'm left with this term. And notice what I have. I need to find the propagator. You see what happens when you use unphysical degrees of freedom. Remember when you did the photon before the gauge fixing, there was no propagator. And here I have a funny thing that I am mixing the different Lorentz degrees of freedom, and it's a real mess. So I don't like this term that Hoff says. So when I choose my gauge, I don't want to have this term because I want to be able to find the propagator. Notice that this term cancels the mixing term that Hoff does. This is introduced to cancel the AG mixing so that you have a clean form to find the propagator. The same way they introduce in QCD this term killed the transversality property of the quadratic form, and you could the projective, and you could find the propagator. Okay, so see what we achieved. See, cancelled, we got rid of that. So what we have, in other words, we are talking about the free GA system. I didn't look at the interaction. I have to find the propagators, okay, the quadratic form. What do I get? Here, I have the G Lagrangian, which is 1/2 d mu G squared minus C 1/2 ma squared G squared. If you, where is it? Here. Let's check it. This came from this term. It checks. Then I have, and A is now separate. How does the A? There is a F mu nu piece. What else? There is a 1/2. There is a Proca piece. And something else. So that double checks. What else is there? I think I have missed something. There is the gauge fixing term. It's very important, 1/2 C. d mu a mu square. You have done the piece for you found the propagator without a mu, you knew how to do that, you did your homework. I can see a number of you sending the, I don't know if it was all of you. So you will also know how to do this. It's the same calculation. So from these two, it's very easy to find d of g. This one is trivial. Let me call the momentum p, sometimes I call it p, minus c ma squared. Notice that g is unphysical, please. M g is square root of c ma. It depends on the gauge. Cannot be physical, as you know. If I take psi equal to 0, g is massless. If I take psi equal to infinity, I don't know, I can choose whatever I want. So this is not a physical field. And of course, it shouldn't be. This is like a longitudinal degree of freedom, or the time like which is propagating off shell. But it's not a physical particle. Just like photon has 2 degrees of freedom, this system of G and A will have 3 physical degrees of freedom. We just got rid of one of them. And the delta mu nu. Here is the, I don't know what name to give it. It could be called a Hoft or something, but that's a matter. In our psi gauge, let's see it like this. We are in our, this is called an arc psi gauge. By the way, this is called arc psi gauge. Arc psi gauge. R stands for renormalizable, you will understand. Psi because psi is there. Psi of c as I call it, and it looks like this. For you to prove it, minus I p square minus ma square. This of course has to be there. This is telling you what the mass of the A is. It's ma. Then there is a g mu nu. Then there is psi minus 1. And I got this, I have to get this right. I think I will. We'll analyze it if I'm right. We'll think about the logic. I think it is correct, but we will check it in the moment. This is a Hopf propagator. This is the renormalizable manifestly. Why do I call it renormalizable? It has all the beautiful property of the QED propagator. When P goes to infinity, delta mu nu of C goes to 0 very quickly, goes as 1p squared, goes to 0. Just as happens in the QED. Notice manifestly that there is 1 over p squared. The second p is p mu, it's not ma squared now, it's p squared minus psi ma squared. It's not easy to show that the theory is normalizable. Well, what you have to show, by the way, it exceeds parameter which cancels, the way you did in QED. We'll do a calculation. We'll illustrate that. I may do it, I may give you a homework, but I may be in the mood to do it, we'll see. But you can catch the essence, okay? The loops now are finite. Spontaneous symmetry breaking of a gauge theory is equivalent to the unbroken gauge theory when it comes to the, of course, equivalent, I mean, in the sense of being renormalizable. Of course, the broken one has a massive gauge field, this one unbroken, but they are equally good. We call them renormalizable. Renormalizable means good. You can compute. And you know, the proof is highly non-trivial. You have to show it the way you show in QED, but it's captured here. Once you have a well-behaved propagator, it works. And therefore now you can, let's just study this propagator, okay? This one is very easy. There is nothing d of g we know. You see what d of g will come. There will be a piece from A, depending on C. There will be a piece of g that they will cancel each other because the physical result has to be C independent. G plays a fundamental role. It always accompanies the A propagator. So when you are computing some scattering, you see what I mean? Imagine that you are computing, I add a fermion later on, and you want to compute the fermion scattering. You have to introduce not just A, you must always keep G, and you will see, I will convince you, plus G is independent of C. To be proven. It's very similar to the calculation in QED. It's not a big deal. That you shouldn't be surprised. You've experienced this before. Let's study the AMU propagator a little bit. Let's go back. Let's see if I got it right. Look at it. This is the one which is non-trivial. The psi equal 1 at Hooft, who is an extraordinary calculator. It's called Hooft-Feynman gauge. Feynman used to like the gauge in QED. By the way, it's not the same gauge because what you get in this case, delta mu nu of A goes into minus I G mu nu over P squared minus MA squared. In QED, when MA is 0, Feynman used to like to work this gauge, so it became known as the Hooft-Feynman gauge. It's a beautiful gauge to do calculation if you know how to trust, if you're really good, if you can trust yourself. But you don't have a control. You don't know if you're making a mistake. You have to be sure that you are good at calculating. Okay, so some people actually keep the C. And then you, at the end of the calculation, show that they cancel and you say, oh, I probably didn't make a mistake. The psi equals 0 is very interesting. In this case, this is sort of like, you know, used to be called Landau in the old days in QED. Delta mu nu over 8. Let's see what we get. Minus I that I know is here. Let me check what I get. I think I'm right with psi equals 0. Notice, oh, I don't like the sign. Oh, no, it's good. Psi equals 0. There is a minus sign, precisely as in Landau. I'm sorry. It's good. G mu nu minus P mu nu over P squared. Looks like Landau. I mean, it's not fair. Landau would work with MA equals 0, but he has this transfer property. Notice, please. Psi equals 0. MA disappears, and I have a minus sign. There's an interesting limit, psi equal infinity, or going to infinity, we should say. Look what happens when psi goes to infinity. Can you see, please? Then actually, the psi goes to infinity, it is MA that dominates. So for any finite P, you look psi going to infinity, and you find out, in this case, delta mu nu of A goes into minus I P squared minus MA squared G mu nu minus, let's check again when psi is infinite. I can forget 1. I can forget P squared, psi cancels, and I get minus. I've chosen the right psi, I remembered correctly, minus P nu over MA squared. What does it remind you of? This is the propagator. proca, which we called unitary gauge. In the unitary gauge, this is what we got. In the unitary gauge propagate. So in other words, if you want to do the calculations, you don't work with this propagator because it's a bad propagator. This will never give you a finite. You work with C, and then at the end of the day, you take C going to infinity, but not before. It's like kind of a regulator, the C, making sure that you always get a finite result. You first compute with C, and then you take the limit C going to infinity. Notice another thing also, that what happens in this limit, notice the propagator of G, it disappears. D of G going to 0. Of course, this is what you expected. G does not propagate her. G goes away, which you expected, because in the unitary gauge there was no G. Agrees fully with unitary gauge, with what Weinberg did. Sometimes this can be actually a very useful gauge if there are no infinities. Surely on the tree level, when there is nothing to integrate over, this is a good gauge. There are sometimes situations when infinities cancel, and then you can actually work in this gauge, because it's much simpler not to have this G field floating around. But notice that the way at Hooft work, it's also quite simple and elegant. There is, I should have said that with psi equal 1, there was also, why don't I keep it? D of G goes into I over P square minus MA square. You see, with psi equal 1, I have this sort of massive gauge field, but I also have the G guy that kind of conspired to make the theory work. You never get rid of psi equals 0. In this case, D of G. It's very interesting. D of G goes into I over P square when psi equal to 0. And you see, manifestly G is not a physical field. I choose a different gauge and I get a different mass, a different propagation completely. Again, this I over P square ensures that the physical result is the same as you would get for psi equal 1. Where there was, of course, G, there is also G. In the infinity limit, it's true that G disappears, but there is a full propagator of the Proca field, which has to survive, because in the unitary gauge, we simply eliminated G. It's amazing what a choice of variables can do. I know, of course, I didn't prove to you that the theory is well behaved, but at least I've indicated to you, I've shown you the way, I've shown you the road to proving that by giving you the analogy with QED. And now, we have established that the propagator behaves well. If you're really following me, and I can't judge because you're not asking me questions. If you're following me, you're getting to the crux of what lies behind the great success of the standard model spontaneous symmetry breaking gauge theory. Gauge spontaneous symmetry breaking. This is very interesting, by the way. In 1960, so you see what happened. In 1960, when Nambu introduced spontaneous symmetry breaking in 1960. And it's very interesting. This was at the so-called Rochester Conference. Rochester conferences are high energy conferences, and the whole world comes together every 2 years. Now there'll be almost 1,000 people in the Rochester conference. Oh, if we had it, I don't know what it is, but just to give you an idea, last year we had a neutrino conference, which is not that large. There were more than 3,000 people. It was one of the most beautiful moments. I had to give a closing talk, so it was very, very gratifying to be able to be part of the history in making what COVID did to us with all the trouble. It's helped us to come together in the most democratic manner at all. Even people who had no money could participate. And the way these conferences are organized now, you have a long conference with only a few hours of lectures in the European afternoon, so that US and Asia, Africa and Europe can be together. At Rochester conference, Nambu is suggesting the idea of spontaneous symmetry breaking, and Yang, of Li and Yang, asks Nambu the following. He says, are you saying that this symmetry is broken, this U1? Yes, you got it, says Nambu. But he says, but as if you are saying that also in some sense the symmetry is not broken. Precisely, Nambu says. Man, this is fantastic, okay, the way Yang reacts. And I used to work in Brookhaven National Lab when Yang was a professor at Stony Brook. So we were sister institutions like CISA and ICDP. So we are basically colleagues. And this really describes Yang well. He's very proud of his intelligence and logic. So he tells Nambu, look, let me teach you something. You cannot have both statement and the opposite. You see, something is either like it's black or it's not black. So he says, let me ask you again, are you saying that the symmetry is broken? Yes, they go 3 times. And every time Yang makes fun of Nambu. But you see what we have learned with the work of 't Hooft. Nambu chooses manifestly the variables when the symmetry is broken. He eliminates the unphysical degree of freedom by taking the phase in the unitary gauge. Right? This is what Weinberg does. Here it's manifestly broken. Look, there is no more this gauge symmetry. We don't have G field at all because of the gauge transformation here before. If I don't perform it, if I keep G, then of course G is there. And I wrote you 't Hooft wrote the linear version of that. You can write it exponentially if you like. The end result will do the same because the leading term is this. So in this case, it is sort of, we are going into kind of unbroken. You're pretending that the symmetry is not broken. Coleman, a great physicist, but maybe even a greater divulgator of Sidney Coleman, who was the generation of the extraordinary success of Harvard. There was a time at Harvard when Coleman, Georgi, you'll hear the name of Georgi later, Glesch and Weinberg were the faculty. We are far cry. Coleman used to call it hidden symmetry. What does it mean? That he didn't win, but I think this name would be even better. This is instead of calling it spontaneously broken symmetry. What it means that in the Lagrangian there is a symmetry. So that's what Nambu wanted to say. The symmetry is there, but the ground state no symmetry in vacuum. And since you are allowed to use the variables the which you like, you can sort of work in a broken phase, or you can work in the phase, you can use any gauge that you like. And so your lesson is that which gauge you use depends what you want to do. If you want to understand physically what is going on, use unitary gauge. If you want to do the calculation, please don't do unitary gauge. You choose, but not unitary. It will drive you crazy. You will get infinities, as Weinberg was driven crazy for basically 5 years. I stop here. Please, if you're in the mood, when you have a few minutes, don't wait for the homework. Try to derive it. I will be curious if you have a problem deriving this propagate. Okay, the G propagating is trivial, but A is similar. This may be, you know, a nice, I don't know whether we'll include it in the homework. I have to think now for the, I'd like you to do the WDK. Okay, seems that there are no questions. I continue being clear, or it's not clear at all, I won't know.
Yes, I have one question.
Hey, good.
You said that for calculating the scattering amplitudes, we need to use also the G propagator.
Right, if you do loops.
Yes, and at the end, we'll have something which depend on this D propagator. At the end, it will cancel out with any other. I mean, it should, but
Right. This is what we have to. We'll do a calculation. This is actually that I show you. We have to show how G plays a fundamental role in canceling this psi dependence. Right? Psi is not physical. This is just a gauge fixing, and therefore it will be crucial. Right? Well, look, I won't do it at the loop level because it will be very long. Let's do the tree level. I'm gonna do it actually at the tree level. But the principle is the same. Show how G plus A give you psi independent result. And it's very nice, you know, seeing it on an example, it's to me more illustrative than proving a general theorem. There is a magic of how Xi cancels. We'll do more than that. We will then try to understand how you go from the Higgs mechanism to the Goldstone mechanism and so on. How do I recapture? I mean, if I get rid of the gauge symmetry and I make it global, how do I regain my G field? I'm saying it's not physical. I can even get rid of it. But when I go to the case of constant alpha, it should come back. There's a very strange, you know, little miracle magic. And we want to see that, you and I.
and another question.
Yeah, please.
Can we sort of use the superficial degree of divergence to know if the theory is also renormalizable in a way?
You mean to use the kind of
Counting the
that's what you do, right? I mean, that's what I pretend I'm proving. That's what I'm claiming when the propagator is good, that you expect it to work. You agree? I mean, it's not really proof, but it's a nice indication that this could work. In QED, of course, MA is 0. But when I'm at a large momenta, I'm actually using this to convince you without going into formal mathematical proof, which is not trivial. But I feel very good with these kind of things that Hopf kind of takes me there. When the problem of ultraviolet divergences is the limit when P goes to infinity. When P goes to infinity, MA becomes negligible. So when P goes to infinity, I'm kind of back to QED. It's not surprising that the spontaneously broken theory works well. Broca couldn't. Because there is no way of, we have these unphysical degrees of freedom that the Higgs carries around. So that's precisely your question is, touching into the heart of the thing. That's precisely what I want to argue. That what we have achieved by this arc psi gauge, which when P goes to infinity, which is the source of trouble in field theory, the famous ultraviolet divergences. This is the ultraviolet region, P very large. What happens is that MA, this is equivalent, that MA being very small, because what appears there is MA over P, right? If I go to the energies, I'm M. So just to say MW, I don't know, is 80 GeV or something. Imagine that I'm doing an experiment and the energy, which is 10 to the 10 GeV. Of course, I'm not doing that. Then who cares that MW has here MW is 0. But even if I'm LHC, when the energy is some 14 TeV, again, MW is much smaller than E, and it basically disappears to the leading order. So the arc psi gauge kind of tells you, look, don't worry, the fact that the guy is massive regarding the ultraviolet divergences is irrelevant. To me, this is highly convincing that I should then prove it to all others. Remember what Schwinger and Feynman and Tomonaga did was not to prove it to all others, okay? They kind of used the one loop simple argument to show the cancellation of Xi and the finiteness of the analog of the cancellation of Xi. It was Dyson that then completed it. So people that completed it, Hopf work were Hopf and Weltman and other people that joined the program. But I think here, I would say, this guy has basically the same propagator as the photon when MA goes to 0, which is the situation when P goes to infinity. And therefore, I feel good. I don't need to see the loop to all others. I'm not a formal field theorist. If you are, of course, you want to see that. You thrive on. I don't need that. I need to get a physical thought of raison d'etre, or the physical principle, the physical picture. Then I'm happy, and I'm of course. Anyway, I couldn't do the justice here to go through formal proofs. I couldn't do it really to reproduce the proof, but we don't anyway. We wouldn't be able to do it, and we will do examples to make us comfortable. More questions? Okay, no more questions. So I see you tomorrow.
Thank you.
Thank you.
Oh, we have to send you the homework. I have to. I have to fix. We didn't meet for the office hours tomorrow, Friday, Monday. Something came up. Makes no difference for you, or it makes a difference? Tomorrow, Friday. By the way, why don't you write to me if you have questions? Let's do it that way. The other way, there was almost no questions. Feel free to write to me. I'm available most of the time, so I can talk to you. I will know on that reason. Whoever needs to discuss with me, please send me an email message for whatever questions that you may have. Then we'll easily meet. Okay. All right. Have a nice afternoon. See you tomorrow.